All right. Now I'm the person standing between you and the coffee break, so I promise I'll be quick with this one. So today I'm going to talk about how we can actually learn to control AMAT systems solely from observation via offline reinforcement learning. As a quick outline for today's talk, first I'm going to give you a brief introduction and a motivation for the topic. Then we're going to have a look how we actually can learn learn to control AMAT systems from observation. And then I'm going to talk about some specific aspects that we actually need to consider if we want to do offline learning in hierarchical policies, such as the ones that we consider today. And then I'm going to finish with a conclusion. Okay, so far in the talk that we presented, where we wanted to learn some deep reinforcement learning agents, we looked at online learning algorithms for control. So we have an agent that learns by freely interacting with an environment until it basically learns a policy that is effective. And this type of learning paradigm is extremely expensive, and one could even say infeasible within real-world systems. Just think about having an untrained agent freely interact with your real-world transportation system and just trying out actions for the main purpose of exploration. So what people usually are resort to doing is, instead of letting your agent freely interact with the real-world system, they would train this agent in simulation. And in order to do that, you first need to develop or calibrate a complex simulator of urban mobility, which is usually in itself already a challenging task. And then once you have developed your simulator, you can train your agent by interacting with this simulator. However, online RL algorithms are still very sample inefficient, so it requires an extensive amount of experience to learn an effective policy. So you would need also an extensive amount of interaction for your agent to learn the policy. And then, unfortunately, usually one training won't be enough. You won't necessarily already observe the performance that you wanted to have in your problem setting. So you would probably go back, adjust some parameters in your policy or in your network, and start the training again. And in this setting, you would basically throw away all of the collected data that you collected in your first training and start the training from scratch. So yeah, that is clearly a very data and time inefficient way of learning an agent. And on top of this, after you have finally trained an agent that you're satisfied with, and you want to deploy it in the real world, you would usually observe that the performance doesn't directly transfer from simulation to the real world, as usually the simulators don't have a high enough fidelity to the real world. Okay, so is there an alternative and a more data and time efficient way of training reinforcement learning agent? And in fact, there is, because we can actually also learn to control the AMOD systems solely by using historical data and not by using online interaction. And this is what we basically proposed in this work, to use offline reinforcement learning to train our agents solely offline, to on one hand eliminate the need from learning from scratch, and also to from learning in simulation. And yeah, so the first step of the offline RL workflow is pretty similar to the online RL workflow. We have to collect some data. But the main difference here is that this data can be collected by any behavior policy by either. So that might be by an optimization-based policy, by a heuristic policy, basically whatever the current service provider is using to control its current system. So usually the service provider already has access to a data set of historical decisions controlling their system. So we can then use this data set to learn an agent without any interactions with the AMAT system to achieve a policy that matches or even outperforms the policy that we use to collect this data set. And here we can pre-train the agents, obviously also several times. We can adjust the parameters, do some hyperparameter tuning until we have stable learning. But we can retrain basically using this same data set and don't have to recollect data again and again, like in the online learning setting. And finally, once we have a policy that is pre-trained and safer and cheaper to deploy, we can actually allow for online interactions with the environment, to allow for further online fine-tuning to basically close any potential performance gaps to online RL. And this way, we can basically avoid all of these expensive fleet management decisions that an agent would do in the early stages of training, just for the purpose of exploration. Okay, so the question that arises here is, of course, can we just use online RL algorithms that we use so far for this problem? And Well, the answer is theoretically yes, you could use those algorithms, but there is one fundamental problem, which is that online RL algorithms are designed in a way that they need to have this online interaction to correct for wrong estimates. And what I mean with that, imagine you have you want to train an agent to learn how to drive autonomously, and you have a data set which consists of a car following a road. And now the policy is wondering if driving the car off the road is a good action or a bad action. And in the online RL case, the policy would simply just try this action, crash the car, and realize, okay, this is actually a very bad idea. But in the offline case, we actually don't have this possibility to do this. So offline RL algorithms have to specifically account for these kind of unseen actions in the data set, while at the same time allowing some generalization to behaviors that are better than the behaviors seen in the data sets. So what we want from offline RL algorithms is, just to give you like a high-level intuition, first, of course, find the best behaviors in data sets and filter out the bad behaviors in data sets. Then generalize the best behaviors to similar situations that we've seen in the data set. And then finally also stitch together different parts of good behavior to hopefully combine it to a better behavior. And yeah, we don't have time to go into the detail in how the methodology works, because by now there's actually a large variety of offline RL algorithms. But if anybody's interested after this talk to kind of get a brief overview, I can really recommend this survey from 2023. Okay, I'll be a bit quick on these sets of results. Here we evaluate our offline RL algorithms using real-world trip data from 3 different cities. And we benchmark it against heuristic methods and also the traditional NPC control-based methods. And I think the most interesting comparison here is the offline RL one, which is the CQL algorithm, compared to the online RL one, which is the SAC algorithm. And we can see that basically we achieve performance close to online methods. And interestingly, we could also observe an up to 20 times improvement in sample efficiency. So the offline RL algorithm needed up to 20 times less data to achieve this performance compared to the online RL algorithm. And then we'll be wondering what makes the data set good for offline learning and what doesn't. And we collected different data sets with different behavior policies. And we could observe actually a kind of counterintuitive result, which, for example, in this data set, the medium data set, which was collected by the worst performing behavior policy, we could actually see that we reached the best performing offline RL agent. So we were wondering, okay, why is that the case? As apparently behavior policy performance is not a really good indication for data set quality. And the reason is actually lies in the coverage of the data set. Yeah, I know I'm being a bit fast here because I think the second set of results is a bit more interesting. But here we can basically observe in the medium data set, which is the blue one, we can see we have a really high coverage of action distributions in the data sets. So basically the agent just has a large variety of actions to learn from and therefore also can learn a better policy. Okay, so just take a step back. Why did we even do all of this? Why did we do this online training on a data set? With the main goal of, in the end, doing online fine-tuning and deployment in our real environment. And this is what we did. We compared here in orange the offline pre-trained policy when we do online fine-tuning compared to training from scratch. And we can clearly see how sample efficient the online RL is compared to offline RL, and how offline RL basically is able to learn policy initialization that already starts with a very high reward region and is inherently also less stochastic, as we already did some pre-training. Okay, so far so good. We could show that now with offline RL, we could learn policies initializations that are leading to safe and robust online fine-tuning to control our AMOD system. But actually, there has been one aspect that we kind of ignored so far, or I would say we kind of cheated a bit to learn those policies. And here, just as a reminder that we're using a hierarchical policy, so basically the policies that Daniele presented previously, where we learn a high-level policy that outputs this desired idle vehicle distribution across the network. And then we use our low-level optimization policy to transform this desired idle vehicle distribution to the actual vehicle flows across the network. And when we now want to train this policy offline, we obviously need to have access to a data set that consists of these high-level actions. So of these actions that are the desired idle vehicle distributions across the network. However, when we now have a service provider that is currently running some sort of optimization-based policy or heuristic policy, what they would observe is just the vehicle flows across the network. Obviously, they won't observe this desired idle vehicle distribution that we kind of constructed for our offline RL agent to learn on. So we need a way to kind of transform this low-level data set into this high-level data set to actually enable offline reinforcement learning in these hierarchical policies. And to do that, luckily, we can leverage our knowledge of this low-level optimization policy and solve basically the inverse problem of our forward problem, where instead of transforming this desired distribution into the flows, we can actually find this desired distribution that would lead to the observed flows in the data set. And therefore, we can use this inverse problem to transform this low-level offline data into a high-level data set that we can actually use to train our hierarchical offline RL agent. Okay, but then, just to make it easier to present the results, we call this approach Ohio, which is short for offline hierarchical RL via inverse optimization. Okay, but then looking at all of this, basically we're starting with a data set consisting of flows. We're transforming those flows into high-level actions and then training our agent and then deploying the hierarchical policy online. One could, of course, start wondering, is this even worth it? Or can't we just train an agent directly on this low-level offline data set, which would basically be traditional end-to-end RL. We train an agent to directly control the low-level vehicle flows across the network, which is basically also what we observe directly in the data set. Yeah. And this is what we were asking ourselves when we did our experiments. We collected 4 different data sets. 2 were optimization-based rebalancing policies that were often used in literature, and 2 are heuristic-based policies. And then we trained several algorithms on them. First, we evaluated, of course, online RL algorithms, then simple behavior cloning algorithms, which aim to just mimic the performance in the data set. And then lastly, offline RL algorithms, which aim to hopefully learn something that is better than the performance seen in the data set. And yeah, if we're now going through these results step by step, in online RL, we can actually see how the end-to-end one, which directly needs to control all the vehicle flows across the edges, really suffer from scalability issues. So it's not able to learn a policy that reaches positive profit. So it's still in the negative profit area, even at the end of training. Whereas in the case of our hierarchical policy, we can learn something that is close to Oracle performance. Then interestingly, when we now look at the behavior cloning results, that end-to-end is actually benefiting from having a data set that consists already of reasonable flows. So it's actually learning a policy that is somewhat effective, but it's still worse than the behavior seen in the data set. Whereas in the case of the hierarchical policy, we can actually see that we are matching the performance seen in the data set. So we can see we have like effective imitation learning here. And moving on then to the offline RL results, we can actually somewhat surprisingly see that in the end-to-end case, the offline learning results are even worse than in the behavior cloning case, which is mainly due to the fact that learning a value function for these high-dimensional action spaces is very difficult. Whereas in the case of the hierarchical policy, where we have this reduced action space of the desired distribution, we can actually see that we are able to most of the time improve over the data set performance policy, which is our overall goal of using offline RL. When we now want to kind of zoom in on the performance of the policy behaviors, now we look at the data set that was generated by one of the optimization-based policies. And we can see in the case of the end-to-end policies that we are not able to outperform the dataset policy in both cases. And actually, in the case of the offline RL, we can actually see that it almost stops rebalancing at all. So there's hardly any rebalancing cost here because it fails to learn an effective policy. Whereas in the case of the hierarchical RL, we can basically observe the performance that we would expect if we have successful and effective learning. In the behavior cloning case, we're kind of matching the performance of the behavior policy. And in the case of offline RL, we're actually able to even outperform slightly the performance of the behavior policy by serving more passengers with the same rebalancing cost. Okay, but again, the main goal of offline RL is, of course, to learn a policy that is that serves as an initialization for safe and robust online fine-tuning. And if we look at the fine-tuning results using this hierarchical framework, we can basically see that here on the left is the same city scenario where we trained on one city and then we do the fine-tuning in the same city. And we can see that first, we're basically skipping all of this initial exploration phase of online RL, but also we're consistently above the behavior policy performance. So that means that if a service provider trains offline RL on its data set that was used by using the behavior policy, and then we do online fine-tuning, it will always be better than what they were doing before. And then to stress test our policy, we even evaluated it the same way in a transfer learning setting where we trained it on one city in an offline data set and then allowed for online fine-tuning in a completely different city. And here we could observe the same results that even their offline RL is able to skip a lot of initial training of online RL. Okay, but last but not least, now it's also the question, how does this compare to using end-to-end versus using the hierarchical policies? And yeah, we could clearly see that by using the data set, it was kind of able to learn somewhat an effective policy. But as soon as we allow for online fine-tuning, you can see in both cases, the policy here in purple completely crashes, which we mainly attribute to the fact that the end-to-end policy overfits to the dataset actually. So it's not actually learning to do effective control of the AML system. It's just somewhat learning to mimic actions that are seen in the dataset, but it's not able to generalize and to be robust to actually allow for online training. Okay. Already coming to the conclusion here. The research on system-level control of AML systems previously usually focused on developing the reinforcement learning approaches via online data, while we propose to use this hierarchical approach of combining optimization and offline RL to learn how to control AML systems via offline data. And in doing so, we first identified this quality diversity trade-off of the data set that influences the performance and generalization capabilities, and showed that the hierarchical framework significantly improved scalability and robustness, especially during the online fine-tuning process, where we showed that we, using this kind of hierarchical framework of having a lower level optimization policy, we could allow for sample-efficient fine-tuning, which is specifically very robust and less stochastic to avoid basically all those expensive decisions that an untrained agent would make in the environment. And yeah, since we already saw that somewhat this hierarchical RL really is a very good approach to allow for this online fine-tuning capabilities, in future work, we're planning to kind of look further into this role of the lower level optimization for these safe and robust online fine-tuning capabilities. And yeah, I think I skipped a bit much because I was a bit faster, but at least now we are almost in time for the coffee break. But of course, feel free to have any questions. I'm happy to take any questions if there are any, or we can talk during the coffee break, of course.